We're back again. This time, before we get into proving things, I just want to talk a little bit about different types of statements and different names that we might give them depending on their importance. And I want to talk about a few definitions that we'll use so that we can actually prove something interesting. So we need some definitions so that we can talk about what objects might do and how we might prove that certain objects do those things. Okay, so this is after logic, at least the logic we need to start proving things, but before we actually start proving things. So here are some types of statements. So most fundamental is an axiom. So an axiom typically in mathematics is going to be a statement that we accept as true without proof. So there's usually something very, very fundamental. Okay, we don't have a lot of these, but as I said, very, very fundamental things. Now, we'll also have things that we'll call facts, and facts are just going to be things that we accept as true, but we won't bother proving in this course. And so typically these follow from our axioms, but as I said, we're not going to prove them. So here's an example of both of these things. So it will take as an axiom the following property of integers. If we take two integers, m and n, then minus one of them is an integer, the sum is an integer, the difference is an integer, and the product is also an integer. So we won't have to prove these things. We'll take these things as facts. So if we have two integers, we'll accept that their product is also an integer. Okay, so there's basic properties of the integers. Now, a fact, which we could prove from various things that are typically taken as axioms, is that if we take any real number, then its square is non-negative. Okay, this is something that we could prove from an axiom, but we're not going to for this course. We'll just accept that the square of any real number is not negative. Okay, so these are very fundamental things, and we won't have a lot of them, but they'll be very useful. Let's go on to some other types of statements. So at the top of the chain, I guess, is a theorem. And this is typically an important true statement. So this is something like, very famously, Pythagoras' theorem. Okay, so this will be something big and important that we prove, typically from smaller results along the way. Now, following from a theorem is something we call a corollary. So corollary is a true statement that follows from some previous theorem. So this is usually something interesting that comes as a fairly direct consequence of a theorem. Now, in order to get to theorems, we'll typically have small results that help us prove the big result of the theorem, and these are called lemmas. So a lemma is a true statement that maybe isn't so interesting by itself, but helps us prove something more interesting. And finally, a lot of what we do will just be results that we're proving to practice proving. So we'll call these results or propositions, and these will be true statements that we prove, especially as exercises or demonstrations, examples, that we'll call results, and maybe if they're a little bit more important, we'll call it a proposition. And so the idea of these is just things that we're going to prove to get practice proving things. Okay? Now, if we're going to start proving things, we've got to have some definitions that tell us what we might be proving. And so let's start off with something very, very basic. Let's just give a firm, rigorous definition, precise definition of what it means for numbers to be odd and even. So we'll say that an integer n is even if n is 2 times some other integer. So notice an integer as n is even if we can write it as 2 times some other integer. Similarly, an integer is odd if we can write it as 2 times an integer plus 1 for some integer. Now, typically, actually not typically, we will say that if two integers are either both even at the same time or both odd at the same time, then they have the same parity. If they have different, if one is even, one is odd, then we'll say that they have opposite parity. So these are just terms that we use to describe things being even or odd. And as we know, an integer is either even or odd. It can't be both and it can't be neither. Okay. So notice something in this definition here. The word if appears. So in this definition, and indeed typically in definitions, when we use the word if, we really mean if and only if. Okay, so we really mean here not a logical implication, we mean that n is even if we can write it as 2 times something, but also if we can write it as 2 times something, then it's even. So the logic flows in both directions. So in a definition, we typically use if to mean if and only if. And this is just a quirk of how we write definitions down. Now, something else we should say here, because this has come up a few times when I've taught this course, the number 0 is actually even, because 0 is 2 times 0. Okay, so it's twice the integer 0. Now, the reason I bring this up is I have had students come to me and ask this because in school they were taught differently, that 0 was neither even nor odd. No, 0 is definitely an even number. Okay, some more useful definitions also on the theme of sort of divisibility. Let's take two integers, n and k. We say that k divides n if we can find some other integer l so that n is l times k. Okay, so that we can write n as the product of k and some other integer l. So in this case, we'll write this notation, so k vertical bar n, to mean k divides n. And we'll say that k is a divisor of n, and at the same time, n is a multiple of k. Now I know I'm not telling you anything here that is particularly new to you, but what I want to take away from these definitions is just very, very precise language. Because sometimes you think about k dividing n to mean, oh, I can divide it with getting a whole number out. Okay? The definition is maybe a little bit ambiguous, a little bit soft. If we write it like this, then we can have a very firm, precise definition that we can use very carefully when we prove things. Okay? So we need our definitions to be very precise. Okay? Going on from this, as soon as we learn about division, we typically come across the idea of primality, about primes. So we say that a number n is prime, and I should really have highlighted that word in writing this definition. We say the number n is prime when it has exactly two positive divisors, namely 1 and itself. So for example, 3 we can only write as 1 times 3. We can't write it any other way as a product. Now, if n has more than two positive divisors, we say that it's composite. So for example, 4 we can write as 1 times 4, and we can also write it as 2 times 2. So it has divisors 1, 4, and 2. Okay, so that's composite. Finally, the number 1 is neither prime nor composite. The number 1 is strange in this definition, and we take it to be neither a prime number nor a composite number. It's, I guess, what we call a unit. Okay. A little bit more, all on the topic of divisibility, because this is what we're going to use to prove things, to get used to the idea of proving things. If we take two integers a and b, the greatest common divisor of a and b is the largest positive integer that divides both a and b. So the biggest integer that divides both a and b, the greatest common divisor. On the other hand, the least common multiple of a and b is the smallest positive integer that is divisible by both a and b. So for example, the GCD, greatest common divisor of, let's say, 4 and 6, is going to be the number 2. Because 2 divides 4, 2 divides 6, and nothing bigger divides 4 and 6. On the other hand, the least common multiple of, say, 8 and 6, well, let's think a bit here, this is going to be the number 24. Because 6 divides 24, 8 divides 24, but nothing smaller is divisible by 6 and 8. Okay, to check that for a moment in my head, but I'm pretty sure that's true. And we denote, as I have just here, the greatest common divisor by GCD and the least common multiple by LCM. Okay. Another definition, I apologize, we're going to get all of these little definitions out of the way because we'll make use of them as we go. Actually, this isn't so much a definition as a useful fact. Okay, so as we talked about a little bit earlier, we have some facts that we're going to make use of. Euclidean division. Okay, so it's just a name given to something that you've been doing for a long time, namely when you divide a number by another that you get a remainder, and that you can do this in a unique way. So if we take two integers a and b with b strictly positive, then there exist unique integers q and r, so that I can write a as a multiple of b with some remainder, and I'm going to do it, indeed, that's how we get the uniqueness, by constraining that remainder to be between 0 and b. And by constraining that remainder to be between 0 and b, I get uniqueness here. Okay. Finally, talk about congruence modulo n. All of these things have the flavor of divisibility. So let a and b be two integers, and let n be a natural number, so a positive integer. We say that a is congruent to b modulo n when n divides the difference between a and b. Now, in this context, n is called the modulus, and we write this congruence as this. A is triple equals sine b modulo n. When n doesn't divide this difference, we say, sort of unsurprisingly, that A is not congruent to B modulo n, and we write this same expression but now just with a stroke through the triple equal sign. So, for example, 5 is congruent to 1 mod 4 because 5 minus 1 is 4. 17 is congruent to 1 mod 4 because 17 minus 1 is 16 mod 4. But 3 is not congruent to 9 mod 4 because 3 minus 9 is minus 6 and 4 doesn't divide that. Okay, so that's a lot of definitions and bits and pieces, but we're going to make use of these in a moment when it comes to actually proving some things. And I'm going to stop there.